Hi everyone, third lecture about carboxylic acid derivative, and our subject today is introduction to nucleophilic acid substitution. The characteristic reaction of the carboxylic acid derivative is nucleophilic acid substitution. That meaning the main or the important reaction for the carboxylic acid derivative is the nucleophilic acid substitution. This is the general reaction that occur with both negatively charged nucleophile with negative charge, or with neutral nucleophiles, with nucleophile like water, like alcohol, like ammonia. All of these examples is neutral nucleophiles. And the main idea here is to remove the leaving group and put the nucleophile. Okay, the carboxylic acid derivative react with nucleophiles because they contain an electrophilic anhydride carbonyl carbon. That meaning this carbon here is electron deficient, partially what? Positive. That meaning the nucleophile like to attack or lovely to attack this carbon. And also with the with sp2 carbon, you know the sp2 carbon, not sp3, always is less hundred or unhundred. Then the substitution occur, not addition. We don't say addition. What is the difference between addition and substitution? Addition, that meaning the new group, it will be added to the structure without any removing group. But here no, we have to add the nucleophile and remove the leaving group. For this reason we said substitution occur, not addition, because carboxylic acid derivative have a leaving group. There is a leaving group in the structure. And for more understanding to this reaction, we have to understand the mechanism for this reaction. And the mechanism for this reaction is two-step: nucleophilic attack followed by lost leaving group. Step number 1, nucleophilic attack. The nucleophile will be attack the structure. And step number 2, the leaving group, it will be removed out from the structure. And here look, the nucleophile attack the carbon of the carbonyl group, and the pi bond, it will be open. Step number 2, the negative charge, it will be make a new pi bond, and the leaving group, it will be removed from the structure to give you the product. The overall result of the addition nucleophilic and elimination of the leaving group is substitution of the nucleophile for the leaving group. That meaning overall the process is what? Just nucleophile, it will be replacement with the leaving group. That meaning remove the leaving group and put the nucleophile. This overall the process. That meaning as a reaction is easy to draw the product, but the mechanism is slightly difficult. Then I said before that we have two types of nucleophile. Maybe the nucleophile, it will be neutral, or maybe the nucleophile, it will be with the negative charge. Look here, with this nucleophile minus OH group, this is a nucleophile with negative charge, and look to the water alcohol is neutral nucleophiles. Carboxylate anion, nucleophile with negative charge. Look to the ammonia, the ammonia, also the primary amine, secondary amine, all of this is nucleophiles, neutral nucleophiles. And be careful, the nucleophile must be negative charge, or there is unshape of electron. Then what will be happened if the nucleophile or the atom of the nucleophile is not like the atom of the leaving group. Look to this example here. The leaving group here is a chlor, yes, chlor atom, and the nucleophile with what? With nitrogen atom. What will be happened here? That meaning the carboxylic acid derivative, it will be changed from one to another. That meaning the nucleophile acid substitution using heteroatomic nucleophiles. What meaning heteroatomic nucleophiles? That meaning the atom of the nucleophile is not like the atom of the leaving group. Result. What a result? Result in conversion of one carboxylic acid derivative into another. Here we have acetic chloride derivative, and the product is amide derivative. And here we have carboxylic acid, the product is ester. Each reaction result in the replacement of the leaving group by the nucleophile regardless of the identity of the charge. There is charge or no on the nucleophile. To draw any nucleophile acid substitution, there is main 3 steps. Step number 1, find the sp2 hybridized carbon with the leaving group. Okay, now look to this structure. For example, where is the sp2 carbon? Of course not this, because this sp3. This carbon, yes, sp2, and this not carbon, is halogen. Okay, this oxygen, no, there is, that meaning the sp2 carbon is here. That meaning the substitution will be happened here. Identify the nucleophile. Where's the nucleophile? This? No. Why? Because if you remove the CH3 minus, it will be not stable, because the carbon is low electronegativity. Okay, now where is the leaving group? This? Yes, this possible to be leaving group because the halogen is high electronegativity atom, and it will be go out from the structure with the negative charge, and it will be stable. Okay, now substitute the nucleophile for the leaving group. That meaning you have to remove the nucleophile, remove the leaving group and put the nucleophile. And here he said with neutral nucleophile, a proton must be lost to obtain the neutral substitution product. Put 2 lines or 3 lines. This is important. We said we have 2 types of the nucleophile. We have neutral and negative charge. With negative charge there is no problem here, but with a neutral nucleophile we have additional step. The benefit of this step to remove the proton to give you neutral substitution product, we will see in the next slide. Now the homework here, draw the products of each reaction. Just replace the halogen with the CH3O, and you have a side product HCl as side product, and the product here, that meaning the product it will be here ester. And look to the reactant, you have ester compound, and the product it will be amide compound with ethanol as side product. Then try to write the structure here and here, the structure of the products. Relative reactivity of the carboxylic acid and their derivative. Here the better the leaving group, the more reactive carboxylic acid derivative is a nucleophilic acid substitution. What meaning that? Okay, now you have acetic chloride, yes, and you have amide. The acetic chloride with halogen leaving group, with the chlor leaving group, and the amide with NH2 leaving group. Now, anyone is good leaving group, the halogen or the amine? Of course the halogen. Why? Because the halogen is high electronegativity and it will be a stable nucleophile. Now, for this reason, the carboxylic acid derivative with the halogen leaving group, that meaning we talk about acid chloride, it will be more reactive than NH2. Why? Because it will be easy to remove from the structure. Yes, the halogen atom, it will be easy to remove from the structure than the NH2 group. And the halogen for the acid chloride, and then we have the anhydride, it will be more reactive than ester or carboxylic acid or the amide. And then we have the ester and the carboxylic acid, they are slightly similar. And finally we have the amide. For this reason, increase the reactivity, it will be from the left to the right, from the left to the right. That meaning most reactive carboxylic acid derivative is the acid chloride, and then the anhydride, and then the ester, and then carboxylic acid compound, and then the amide. Based on what? Based on the based on the properties of the leaving group. Then he said here, based on the order of the reactivity, more reactive acyl compound, look, more reactive acyl compound, the acid chloride and the anhydride, both of this and this, can be converted to less reactive one. That meaning if you have acid chloride or anhydride, it will be can be converted to the ester or carboxylic acid or the amide. And the reverse is not usually true. But if you have amide and you want to prepare the anhydride or the acid chloride, it is usually not true, or cannot be prepared from less reactive one to the more reactive one. Maybe just by using a special catalyst and special conditions. Then, to see why this is so, يعني why the less reactive carboxylic acid derivative cannot be prepared from the more reactive carboxylic acid derivative. Then, to see why this so, recall that nucleophilic addition to carbonyl groups from the tetrahedral intermediate with two possible leaving group, Z- or the nucleophile. Look, if you put the nucleophile here, that meaning that your intermediate will be this tetrahedral intermediate, and you have this leaving group and this leaving group. Now you have to remove this or this. The group that is subsequently eliminated is the better of the two leaving group. That meaning if the product remove this leaving group, it will be better than this. For this reason, your starting material, it will be more reactive. Okay, for a reaction to form substitution product, therefore Z- must be better leaving group. Make the starting material, the starting material is more reactive acyl compound. Okay, then if you have here Z halogen chlor and the nucleophile is NH2, okay, that meaning it is possible to give you the nucleophilic acyl substitution. Why? Because the acid chloride is more reactive than amide, and we can convert the more reactive compound to the less reactive carboxylic acid derivative compound. Again, to evaluate whether the nucleophilic substitution reaction it will be occur or not, you have to compare the leaving group ability, this is the leaving group ability of the incoming nucleophile and the departing leaving group. Okay, now you have to compare this and this. Anyone is best leaving group. If Z best leaving group than this nucleophile, that means the reaction will be happened. Okay, if the nucleophile more is best leaving group than the Z, that meaning the reaction it will be not happen. Now look to this equation. Determine whether each nucleophilic acid substitution is likely to occur. يعني he mean here this reaction is possible to happen or no, and this reaction is possible to happen or no. Then look, compare the chlor with this nucleophile OCH2CH3, or you can compare the acidic chloride to the ester. Anyone is more reactive. Of course, this is more reactive than this. That meaning this it will be happened and it will be occur. Look to this reaction. The amide is less reactive one, and you have here anhydride is more active carboxylic acid derivative, the anhydride. That meaning we can convert the less reactive to the more reactive. The answer is no. That meaning cannot be occur, and this it will be occur. Okay, and the explanation for this equation here you can read it. Nucleophilic substitution occur when the leaving group Z- is weaker base and therefore better leaving group than attacking nucleophile for the nucleophile. More reactive acyl compounds can be converted to the less reactive acyl compound by nucleophilic substitution. This is important 2 points, and please memorize both of them. And also you have homework here. That meaning in general we will examine nucleophilic acid substitution with 4 different nucleophiles as shown below. Now the first reaction, the nucleophile is the carboxylate anion, and the product it will be anhydride. The second one, the nucleophile is the H2O neutral, or maybe the hydroxyl group minus, and the product it will be carboxylic acid derivative. And the third reaction, we use the alcohol as neutral nucleophile, and the product it will be ester. And the fourth reaction, we use the ammonia and ammonia derivative, the amine compound. And if you use the ammonia, you have primary amide. If you use the primary amine, give you secondary amide. If you use secondary amine, give you tertiary amide. If you use tertiary amine, it will be, there is no the reaction it will be happen, but it will be give you salts, not the amide derivative. Then all of these reactions is to prepare anhydride, carboxylic acid, ester, and amide, not to prepare aside the acidic chloride. Why? Because we say the acidic chloride is more reactive carboxylic acid derivative. It is not easy to convert to prepare from the less reactive carboxylic acid derivative. Then this reaction again are used to make anhydride, carboxylic acid, ester, and amide, but not acidic chloride from other acyl compound. Acidic chloride are the most reactive acyl compound. They have the best leaving group, the halogen, so they are not easily formed as a product of the nucleophilic substitution reaction. Okay, then how we can prepare the acid chloride? There is just a special reagent from the carboxylic acid. That means we have carboxylic acid and a special reagent, and we can prepare the acid chloride compound. Reaction of acid chloride. Acid chloride readily react with nucleophiles to form nucleophilic substitution product with HCl. HCl will be a side product. This is the HCl, it will be a side product. And to remove HCl from the reaction, we already put some base to react with this HCl, and we use usually the pyridine, and the pyridine will be react with HCl to form a salt, and in this case there is no any effect for the HCl to the product. Then the acid chloride react with oxygen nucleophiles to form anhydride, carboxylic acid and ester. Look, you have this acid chloride can be react with this carboxylate anion. That meaning the nucleophile atom here is the oxygen with the negative charge. To form what? To form anhydride, and react with the H2O and also with the oxygen atom to produce the carboxylic acid, and react with alcohol to produce the esters compound. And then acid chloride also react with ammonia and primary secondary amine to form primary secondary tertiary amide. Okay, that meaning if you have acid chloride and react with the ammonia, the product will be primary amide, and with secondary amine the product will be secondary amide. With the primary amine the product will be secondary amide. With secondary amine the product it will be tertiary amide. And look to these examples. We have here this acyl compound. You have acyl chloride here, and the other reactant compound, the second reactant compound, the nucleophile here is secondary amine, diethylamine, and the product it will be tertiary amide. And the mechanism for substitution acyl reactions is the same mechanism. Two-step. If you use the negative nucleophile, two-step addition, tetrahedral, and remove the leaving group. But if you have neutral nucleophile, I said before that you have additional step to remove the proton, to equal the positive charge on the nucleophile atom. Then you can say nucleophilic substitution with neutral nucleophile like H2O, alcohol, ammonia requires an additional step, not just two step, three step. 1, 2, 3 is remove the proton or transfer proton from the tetrahedral structure to the another compound. And the reaction of acid chloride with H2O as nucleophile convert the acid chloride to the carboxylic acid, and the three step. Look here, addition of the H2O molecule, and open the pi bond here, and then we have it will be positive charge on the oxygen. Why? Because the oxygen lost the unship of electron, and in this case it will be electron deficient. Then how we can equal this positive charge? By remove this proton. We use base here by remove this proton. Okay, and then the final step is already same. The negative charge make pi bond and remove the leaving group from the structure to give you the final product. And this homework for you: draw stepwise mechanism for the formation of this compound from alcohol and acetic chloride. This compound is alcohol and this compound is acetic chloride. Okay, and I want from you to draw all the mechanism step by step. You already have 3 steps mechanism. And reaction of anhydride. From anhydride we can prepare already the carboxylic acid, and we can prepare the ester, and we can prepare the amide, primary, secondary, tertiary amide, all of them. Okay, but we cannot prepare the acyl chloride, the acidic chloride from the anhydride. Then the nucleophilic attack occur at one carbonyl, while the second carbonyl become part of the living group. The same mechanism. That meaning you have here 2 carbonyl, yeah. That meaning the nucleophile, it will be attack this carbon, and this it will be living group, or attack this carbon and this part it will be living group. Okay, dependent on what? Dependent on the positive charge here. Anyone is strong positive charge from the other. This and this, dependent on the R group here. This and this. Then look to these examples. You have here H2O nucleophile, and the H2O it will be attack here, and this it will be removed to give you the carboxylic acid product, and we have byproduct is another carboxylic acid, the byproduct. Okay, because this part will be removed from the structure to give you byproduct. And also with ethanol give you ester, and also we have byproduct. And with ammonia also it will be attacked from this side, and this will be removed. That meaning we have amide product and we have side product, byproduct. We have the carboxylate anion as a salt here, carboxylic anion. That meaning if you used water, you have carboxylic acid side product. If you use ethanol, you have carboxylic acid side product. If you use amine, you have carboxylic anion side product. And this homework for you: draw the product formed between benzoic anhydride is treated with each nucleophile, this and this and this and this. Okay, he draw the product. Just I want the products without mechanism. Then the mechanism to convert anhydride to another to the amide derivative is already 3 steps: 1, 2, 3. Why 3, not 2? Again, because our nucleophile here is the amine, ammonia, or primary amine. Okay, neutral nucleophile. For neutral nucleophile we need additional step. This additional step: remove the proton. Remove proton, okay, to equal the positive charge, and give you the amide at the final. And we have here 2 examples how we convert the anhydride to the acetyl salicylic acid, the aspirin, and also acetaminophen. Both of them is drug compounds used for treatment some disease. And I will stop here the reaction of carboxylic acid, and I hope you can ready to study this lecture. And if you have any questions, please join us in our meeting at Tuesday at 11 a.m. and see you later.